Hello. Good morning to you. Welcome to this event which is running today. My name is David Price. I'm Vice Provost for Research here at UCL, and it's my pleasure to welcome you and also to welcome a variety of colleagues from Microsoft today, but particularly we're delighted to welcome Rashid, who is with us and that we'll be hearing from a little bit later on. The role of computer sciences and computational sciences at UCL is absolutely key. We obviously have a major and world-leading computer sciences department led by a variety of great researchers here today, and doing a variety of really world-leading activities in a whole range of disciplines within computer sciences. But also, in addition to that, the role of computational sciences across UCL is also vital. So the applications of modern computing techniques all the way from areas such as digital humanities, through the Thomas Young Centre for Computational Condensed Matter Physics, through our astronomy and astrophysics groups, through the computational biological communities, through computational medical activity, and also, very importantly these days, in the e-health environment too. So as a result of that, obviously UCL is committed large amounts of funding to institutional infrastructure, in high-performance computing, in petabyte data storage capability, and obviously in networking. And we also engaging significant amount of funds into algorithmic development and programming for applications, all from the institutional side of things. So obviously, computational science, computer science is absolutely key for our institutional future and the drive not only for our activities, but for the UK and the developed world, and obviously key part for the future economic growth. So it's great that UCL has an ongoing and developing relationship with Microsoft, and I'll just turn to now Anthony Finkelstein, say a few words to explain in greater detail the nature of that relationship before we start the lectures.
Well, thank you very much indeed, David. I've been thinking for some time about what makes for effective partnerships between universities and industry. It's a topic that I think is definitely worthy of some attention. And though I'm not entirely finished with the thinking, I have already some cues as to what that might be. The first is to do with shared values. And that's something I think definitely that Microsoft and UCL have in common. A global focus, a willingness to look at major challenges, and a drive to excellence. It's important too to share a vision of the subject. In UCL we have a very particular tack on computing and computer science, an approach that is experimental, engaged, and empirical. And that's something which, again, we share with Microsoft Research. Common attitudes of mind are important, an openness to new ideas, a willingness to take risks, and a sort of some cultural similarities which we share with Microsoft. A slight impatience and a strong sense that we have something to prove. We share a common background. We share a common background, a background in the area of systems research. It's something which actually is not common across computer science in certainly in the UK, and is something for which UCL has a reputation and of which Microsoft has proven excellence. And lastly, I think patience, the ability to sustain a relationship over a period of time. And now I think we can say with some pride that our relationship with Microsoft is appearing as a sustained relationship, one in which we are prepared to invest. And that's the last point, really, that point about co-investment. We're very grateful for the investment that Microsoft has made in UCL, and we're matching that We're particularly proud about the, I don't know what, the sort of the sweat co-investment which has gone into it, particularly the staff in Microsoft who are now spending so much time here, Byron, Thore, Sharam, and others. Historically, of course, Andrew Herbert continues to be a very good friend of UCL's. We recognise absolutely the multidimensional nature of the relationship inevitable in universities. A relationship which spans the dimensions of research, but also covers across to education and the use of Microsoft technologies and enterprise engagement with the spin-out and entrepreneurial companies that come out of UCL. At UCL, we possess leading excellence in areas that Microsoft research care about: interactivity, verification, computational statistics and machine learning, computational sciences, and software engineering. I know we possess leading excellence in the area because I've used Microsoft's own tool, Academic Search, to determine that. So where does the future of the relationship lie? I guess Rick may give us some clues as to that in his talk. I believe that there lie further opportunities to exploit UCL's unique interdisciplinary richness, a richness which spans across to the humanities and social sciences, as well as obviously our very strong background in the life and medical sciences. I personally believe that there are some very important, what I would call everyday challenges related to office productivity. The questions about email, about presentation software, about word processing, and so on. Problems which I think are now ripe for a radical rethink. I think just simply putting existing technologies in the cloud, it's not simply, but putting existing technologies in the cloud may be only the first step to a necessary rethink about how office work is done. And I think there's an important future there. I think also the interesting area of interaction with smart environments and the user dimension of what that might mean is an important and interesting area where there's potential for exciting joint collaboration. So with those few words, I will hand back to David to introduce our speaker.
Thank you, Anthony. And indeed, it is my pleasure now to introduce Rick Rashid to you. Rick probably doesn't need much introduction to you in the computational sciences area. He was a graduate from Stanford and then Rochester, and his distinguished career also was at computer sciences at Carnegie Mellon. Since, I think, 1991, Rick joined Microsoft, and since 2000, he, I think, has been the Chief Research Officer at Microsoft Research. His insights and his activities have obviously guided the development of the marvellous achievements of Microsoft over the years, and as we've just heard from Anthony, the close resonance between their objectives and our objectives, perhaps on a slightly different global scale, but we are working on that, are obvious, and therefore it would be wonderful to hear what Rick has to give us this afternoon, or this morning. So, Rick.
Okay, thanks.
You.
I've already got a mic, thanks. I think we're going to start with a video, so we'll do that and then I'll start talking. I think the video does a good job of explaining why I have so much fun running Microsoft Research. A lot of really cool stuff going on. Well, I want to say I really, am pleased to be here today at UCL. I'm glad that all of you have come despite the dire predictions of a snow apocalypse. I thought it was interesting as we were driving into the city, all the signs basically say, go away, never come back, I gather even small amounts of snow here seem to create a certain amount of chaos, so hopefully things won't get too bad. As was just being said, I came to Microsoft in 1991, and before that I was a professor for 12 years at Carnegie Mellon University. I came to Microsoft to start Microsoft Research, so I've been running Microsoft Research from its inception. And strictly speaking, we actually date the beginning of Microsoft Research from the first day I joined Microsoft. So that makes it very easy for me to keep track of anniversaries, and I don't have to worry about that too much. It does mean that I have kind of an unusual distinction within the company because I am the Microsoft executive that's been doing the same job for the longest time. Now, you could argue that, you could look at that in a variety of different ways. You could say, wow, he's evidently really good at what he does. Or you could say, hey, he only knows how to do one thing. And you could decide for yourself which of those two is likely to be the case. It's also the case, it's kind of unusual in a corporate environment for anyone to do the same job for that long. I think certainly of the major research labs I'm aware of, I don't think anyone's ever run one for that long. Emmanuel Priori started IBM Research and ran it for 15 years. But that's one of the longest tenures I'm familiar with out there. So it's kind of an unusual situation, but it's also a great situation to be in because I've had the opportunity to both create an organization like Microsoft Research, but really also to see it grow and see it change and to be able to bring in such amazingly good people over the years. And that's been kind of a personal point of not just pride but enjoyment for me, just to see the organization change over that period of time and to stay involved with it for so long. It also is the case that because I came to Microsoft 21 years ago to start Microsoft Research, I've been running it for the whole time. We've also had the advantage of having exactly the same mission statement for the entire life of the organization. Again, that might set some corporate record, I'm not sure. But I've always had a very, very simple way of thinking about what we did at Microsoft Research. First and foremost, the first part of our mission statement has always been that our goal is to move forward the state of the art in the field of computing. And that's really not very much different than what your goal is here at the university. In fact, I'd argue it's probably exactly the same. And what's interesting about that is that there's nothing about that first part of our mission statement, which is really the most important part, that has anything to do with Microsoft. What it really is saying is that if we engage in research in an area, we want to be able to be at the forefront of that field. We want to push the state of the art forward there. And in some sense, that's more important to us than whether it makes any sense to Microsoft that that's something that we should be doing. And the reason why that's important, and why in some sense it's important that the word Microsoft doesn't appear there, is because unless you're at the state of the art, unless you're really pushing the edge, I don't think the things that we would be doing would be that valuable to Microsoft. In some sense, we want to make sure that whatever we do, we're pushing that edge, and we're making something happen that didn't happen before. And if we had to worry about whether that was important to Microsoft or not, I don't think we would necessarily be doing that. So that's kind of why that part of the mission statement is the way it is. And if you go back historically, there are many times where we've started research areas or engaged in research that at the time we did it had absolutely nothing to do with the company. We started a computer vision group, before there was any product at Microsoft that could conceivably have used the technology. Right, remember, 21 years. PCs weren't doing computer vision back in the early 1990s. We built one of the best computer vision groups in the world long before we needed it. We started one of the best 3D graphics groups in the world, frankly, before anybody else in the company could spell 3D, right? It's just, we believed it was important. We made investments. Some of the technologies you just saw on the screen there in that video, some of the things that went into Microsoft Connect came out of research that was done in the 1990s. It really had nothing to do with anything Microsoft was doing at the time, but we believed it was important. We hired great people that were pushing the state of the art in those areas, and when the time came to that the company needed or wanted to have products in that particular area, we were prepared to help the company do that. So that's the first part of our mission statement. The second part is related to Microsoft. It says, when we have a great idea, I mean, when we come up with something, obviously in research you don't always come up with anything that makes sense. But if we do have something that makes sense, right, then we want to get that out to people as quickly as we can. One of the best ways for us to do that is to work through Microsoft and Microsoft product groups and really try to get that technology out, into the hands of hundreds of millions of people as rapidly as possible. So we work really hard to do that. But that's very distinct from the first part of that mission statement. The first part says, hey, we're going to do great research. And the second part says, if something makes sense, right, and it fits, we're going to get that out to people as quickly as we can. So we don't constrain the front end of the innovation pipeline, right? That goes wherever it needs to go. But at the same time, we try to harvest the good things that come out at the other end and get them out. And in some sense, it all factors into a third part of the statement, which is, and it's not just about Microsoft, it's about the field of computer science. We want to make sure that not just Microsoft has a future, but the field of computer science continues to be vibrant and continues to change the world. Because that's where all the value is going to come from. I mean, as a field, we need to constantly be innovating. We need to be constantly changing. We need to constantly push the edge, because that's where our opportunity to make things happen. And the reason I came to Microsoft was I really wanted to change the world. I wanted to make things happen, and that's really part of it. For an organization that started with just like one person, that was me, we've really grown a lot. And I would never have guessed when I started Microsoft Research that we would be the size that we are today. We've got groups spread out pretty much everywhere, all over the world. We have major research labs in Redmond, Washington, which is where our first research facility was, and it's still our largest. But our second largest group is actually in Beijing, China. Our third largest is here in the UK, in Cambridge, England. We have groups in New York, in Boston, in Silicon Valley, in Santa Barbara, in Bangalore, India. We have a joint research center with INRIA in the Paris area. We have advanced technology labs in Germany, in Israel, in Egypt. We just announced that we're starting one in Brazil, in Rio. The main reason there is I just want to be able to go to Carnival, right? So but don't tell the guys that are working on it. But there's our goal in some sense has been to bring some best people we can into the organization and to be able to have an impact in the areas in which we're doing work. Now, we talked about this discussion a bit about shared goals at the beginning. I'm an extremely firm believer in the value of doing fundamental basic research. Not just in universities, where I've done it in the past myself, but also in corporations. I believe governments need to invest in fundamental basic research. And there's lots of reasons why people talk about, doing basic research. And I think, unfortunately, a lot of times, governments and general population, and even sometimes researchers themselves, are confused as to the value of doing basic research and why we do it, what's the importance of it, how does it change the world in some fashion. Now, there are lots of things that people talk about. One of the things that people always say when they say, well, we should invest in basic research because that's going to produce IP, right? That's going to produce intellectual property that we're going to be able to take advantage of in some fashion. And intellectual property is, in fact, something that great research organizations create. We pursue patents. We build technologies. Microsoft Research it produces about 25% of all the patents that Microsoft gets as a company, and ours are by far the sort of the fundamental ones, the ones that have more of a lasting impact. In fact, the IEEE for many years has said that Microsoft has has the patent portfolio with the most scientific value of any company in the technology field. So we've consistently been able to do that. But while it's a good thing, for Microsoft, it's a good thing for the world that basic research produces intellectual property. I would argue that's not the main reason you do basic research. It's an outcome of doing research well, but it's not the reason to do it. Problem solving. A lot of people. I think when I come to England in the papers, people are always talking about boffins and they're always talking about how people solve all these problems. I think there's a big perception in the globe, in the society as a whole, and that these basic research groups, researchers, professors, and so forth, students, we solve problems, and we do solve problems, and that's really an important thing that we do. It's an important thing that Microsoft Research does for the company. It's an important thing that universities do for society in general. But again, I would argue that's a great consequence of having a fundamental basic research organization. But it's really not the reason you do it. It's one of those good things that happen if you have it. I love solving problems. I love it when people come to me with a problem, and I'll just work on it. I just love doing it because I'm trained for it. Our people really love doing it. But again, that's the consequence of having a great organization, not the reason to have one. Early warning system. People always say, okay, well, the reason you have a research organization or the reason you're doing research in universities is it's ears to the ground. You see the new ideas, you see the new technologies, you can prepare, the company or the country or the whatever organization you're a part of, and that's a good thing too. And again, research organizations do that. But again, I would argue that that's really more of a consequence, an outcome than the reason itself. I think the reason that we exist, Microsoft Research exists, the reason that Microsoft spends hundreds of millions of dollars to do basic research, the reason that countries like the United States and the UK spend huge amounts of money on basic research, is not for those things, although those are all great outcomes and that's really kind of a good thing to have, but it's for this reason. It's that basic research gives you agility, gives you the ability to change when change is really important. So if you go back to the writings of Vannevar Bush in the United States, who's one of the people that really helped to shape the creation of what became the National Science Foundation and sort of the modern notions of funding basic research in the United States, the idea that came out of that, the ideas that he put forward were that we'd just been through a war. There'd been a lot of issues. Technology had been an important part of winning that war. New ideas, scientists had been an important part of that. And he basically made this argument and said, look, we need to invest in fundamental basic research because we don't know what the future is going to hold. We don't know what's going to happen next. And if there's another war, if there's a famine, if there's a disease, right? We need to have the people and the technologies and the ideas that will, as a society, allow us to survive, that will allow us to change if that's important. So that's that's kind of a mental image of it. I think in a company's environment, it's exactly the same thing. The reason we do basic research at Microsoft, the reason Microsoft Research exists, isn't because of all the cool stuff we do, because we do lots of cool stuff, and that's of huge value to the company. And it certainly helps to pay the bills. But the real reason is that when something really goes wrong, right, you've got a treasure chest, of ideas and technologies and people that you can draw upon in order to get you out of whatever the problem is. Let's say there's a new technology, or there's a new competitor, or there's a fundamental change in the business climate. How do you, as an organization, adjust to that? How do you change? I'm going to give you a really simple example. It's not one that gets told very much except by me, so you likely wouldn't have heard of it before, of how a particular set of ideas and technologies had an enormous impact on Microsoft, and the fact that, in some sense, Microsoft is here today. So back in 1992, we were very small, maybe 20 people in research in those days. And one of the areas we've been doing research in was programming technologies and optimization technologies. And one of our researchers, working with some of the other guys in the group, came up with a way of reducing the working set size of 32-bit programs, right? Dramatically, roughly by a factor of 2. Now, for those of you who are not computer scientists, working set size basically means how much memory a program would need to actually execute in. So it's the amount of memory that is needed at any instant in time to execute a program. So we were able to reduce that dramatically. Now, we thought we were this is pretty early on in the early days. We thought this was a really cool result. We started talking with the product teams. And I remember all these meetings really well because I was sitting in all of them, and they were really interesting meetings. On the one hand, the product guys were very excited about what we were doing because it was really cool work, huge amounts of math mostly, to demonstrate how it would function. But at the end of each meeting, with each group, they would generally stand up and say, well, you guys are really smart guys, okay? And this is really cool technology, but we don't actually have this problem, right? Because we don't have 32-bit code. This is like 1992. People had 16-bit code. I mean, very few people were working with 32-bit code back in those days. And besides, we know we're going to switch to 32-bit code, but by the time we do, memory sizes will be so much bigger because everything was doubling every year, so it won't be a problem. But you guys are really smart, so I really appreciate the work you did on it, and I'm sure if you work really, really hard, you'll come up with something we can use. So that was kind of how the conversations went, right? Except for with one team. So with the Windows NT team, this was the team that eventually built what is now the version of Windows that we use. They were building everything in 32-bit code. So we figured, oh, okay, they're going to really like this stuff, right? So we met with them, and that meeting was also really good. Those guys are really very smart, great developers, and they understood exactly what we were doing. They knew that it applied to what they were working on. But at the end of the meeting, the guy that ran that group, David Cutler, who still works at Microsoft, is an amazing, amazing guy. Also a really big guy. Okay, really big guy. I'm not very big. He came up to me. I thought it was a good meeting. I mean, everybody was, we're all talking up. Everything was really great. He comes up to me after the meeting, looks me in the eye, has a very mean face, and says, "You're going to do this to my operating system over my dead body." Okay? Well, needless to say, I mean, the meeting could have gone better. Okay? It could have gone a little bit better. But we believed in what we were doing, and we continued to work in that area, and we actually, improved on the technology quite a bit over the next couple of years. An interesting thing happened in the world, which was that everybody had been seeing memory prices dropping and memory sizes increasing, except right around then, 1993, 1994, that didn't actually happen. Everything went flat. Actually, memory prices actually went up some. Memory sizes didn't increase. There were trade issues between the U.S. and Asia in those days. There was some stories of collusion and whatever. But just that one instant in time, it just didn't happen. And the problem that Microsoft as a company was then facing was in 1995 when we were getting ready to ship our 32-bit versions of Windows and Office. Suddenly, we realized that we were going to have to ship these versions onto computers that hadn't grown in memory size. So a typical computer in those days, and I know this is going to sound really, really funny to you, especially if you're like younger than about 40. But the computers in those days had about 4 or 8 megabytes of memory, right? Not gigabytes, megabytes of memory, and that hadn't changed. And the problem was that was a perfect size for our 16-bit version of Windows and Office, and not surprising, the 32-bit versions took about twice as much memory, and so they just worked like crap. Okay, we weren't going to be able to sell the thing. Good news, we had this technology. Good news, we got a factor of 2 improvement in working set size. Good news, we continued to work on it even though the product groups thought we were stupid. Well, actually, they thought we were smart. They were just doing a stupid thing. And so the consequence was we were able to allow the product groups to ship their 32-bit versions of Windows and Office when otherwise they wouldn't have been able to do that. Now, as a consequence to Microsoft, this made about a few $100 million in additional revenues that year. And Microsoft was a pretty small company back then, right? So a few $100 million was actually like real money. And in fact, and especially these days, of course, everybody talks about trillions of dollars. In those days, hundreds of millions. You could actually take your family to the movie, and we didn't have 3D movies back then, but you probably could have afforded that too. You would pick it up if you saw it on the street. Okay. But so it was a real value to the company. But more to the point, our competitors didn't have anything like this. Lotus and WordPerfect, our Office competitors at the time, they couldn't ship their 32-bit products. They wouldn't work well, right? And even when they did finally get around to shipping about 9 to 12 months later, they still didn't work as well as our products did. And so it was an absolutely enormous competitive advantage to Microsoft that we had that technology. It all had to do with a particular instant in time, right? It was something nobody wanted us to even work on. But it was the fact that we had it and we had the people that knew how to do it, and that particular instant in time came that made that an important thing to Microsoft. And the reason I'm telling you the story is that, and there are lots of stories like that in the history of Microsoft research. The reason I'm telling you the story is because that's the reason you do basic research. It's not for the things that you know you're going to need or want. It's for the stuff you have no idea that you're interested in, but that could suddenly become critically important to the company. Microsoft Connect is another way more recent example where the product group they had a technology that gave them a certain amount of 3D information, and they knew they wanted to be able to track people, but they couldn't make it work reliably. They worked very closely with Microsoft Research in Cambridge and with our groups in Redmond and in Beijing and in Silicon Valley, to perfect that technology, to use machine learning, which really made it work, and to be able to ship it. The company could not have done it otherwise. It was billions of dollars of revenue for Microsoft. So that's why you have basic research. That's why you make those investments. Now, moving a little bit on to the next part of my talk, I'd argue that we're in a period right now where those kinds of basic research investments are even more important because the world is changing really rapidly right now. I mean, many of the things that we could not do before but always wanted to do with computers, we're now on the cusp of being able to do or beginning to see happen. One of those areas is it gets the term big data, but in some sense it's this notion that we can now collect vast amounts of information from many, many different data sources, integrate them together, and start to solve problems, societal problems, scientific problems, in ways that we couldn't have imagined doing before. I'm going to show you a short video of a project that's actually going on at Microsoft Research Cambridge, came out of Microsoft Research Cambridge, called Fetch Climate, where this is work specifically looking at collecting environmental data and being able to make it available to scientists. So let me just show you that.
Hi, I'm Drew Perry. I'm a researcher at Microsoft Research Cambridge on Computational Ecology and Environmental Science Group. The mission of that group is to carry out computational science that should let humanity manage natural resources better. As part of that research mission, we developed new software tools, predictive models, and geographical information services that should allow people to carry out that kind of cutting-edge research more widely. So I'd like to show you Fetch Climate, which is an easy, fast way for anyone to extract complex information about the climate, either just with a few lines of code in the program, or even just through a browser. So here's our browser running Fetch Climate. I'm in Redmond at Microsoft headquarters. So I'm going to zoom in on the area around Redmond, and I can really easily draw a square here with populated grid and hit Fetch. And what's happening is this is a Silverlight application which is communicating with an Azure service. That service is looking over a large number of large data sets, and it's using the best data to answer the query. It's then doing a whole bunch of complex mathematical calculations and sending the results back to our application running in the browser. The answer of that query is now being visualized on top of being mapped by a dynamic data display to another prototype tool that comes from our group. You see that interactivity. We hold the mouse over here. We can see, for instance, that the average temperature in this place is about 2.8 degrees. You can download data. So we just hit download, we get a choice of format. We can see all the information that we would need from that query. It's got different times as well, so we can do a query for a fraction of the year, or even a fraction of the day. And then we have the air temperature data itself. We have the provenance, so the data source that was used to supply this information. And we even have an estimate of uncertainty. That uncertainty is something that the experts find really hard to find data. That was a research project in its own right, and yet that's always supplied every time with Fetch Climate queries. Now we can pull the browser version, we can run multiple copies of Fetch Climate at once. And so I'm going to show you a couple of examples of fetches promoted earlier. So here's one wind speed over the eastern US. That's the kind of thing that you might want to look at if you're an energy company or the government planning wind farms. And in this fetch, I've put a string of locations across Africa, and through each of those locations I've extracted 60 years worth of rainfall data, and we can just hover over one of those points and see what's happened to rainfall. And unfortunately, this looks pretty worrying because it looks like there's been a steady decline in rainfall over the past 60 years, the kind of thing we've probably all seen in the headlines recently, African drought. So thanks to Fetch Climate, anyone can get that kind of information really easily. It's live, it's ready, go and find it, have a go, and please tell us what you think.
So in fact, you can go out on the web and use Fetch Climate if you want to play with it, get a chance to see something about the climate here. It was interesting, I was giving a talk, and I used Fetch Climate as a demo in that talk, and in the demo I did, I specifically was made an example of looking for places you could put a hotel, and have a resort and have it be nice and sunny. And I wasn't really, it was just a random kind of an example. And one of the people in the audience came up to me afterwards and said, "We actually are trying to do that right now. How do we get access to this code?" So there, but I think this gets to the point of the fact that now we can collect data and we can learn a lot of things from it that we might not otherwise have guessed. One of the things we've been doing is working with a small company in the Seattle area called INRIX that has now been deploying technology worldwide to do traffic monitoring and traffic flow. Now that's interesting by itself, and you can go out on the web and use the INRIX tool to do traffic analysis. They do support London area, so it's a great way of doing that. And it's using a lot of machine learning algorithms to come out of Microsoft Research. But more interesting in a way is that we're working with the INRIX guys, and we sort of jointly discovered that this isn't just a way of measuring traffic flow, but it's also an incredibly great way of measuring economic activity, right? Because traffic and economic activity have a lot to do with each other. And in fact, you can look at the changes in traffic flow, and you see before the government sees changes in economic activities in areas in the United States. It was particularly evident as you were looking at the last big recession. And you could get those information signals long before the governments could get the same information, from their data sources about actual economic activity. So there are a lot of things that you can learn, from this kind of data that you wouldn't otherwise get. Another thing that's happening, another sort of area that's emerging right now, is the sort of merging of physical and digital worlds. I mean, in effect, what's happening is that we're entering a period in which we're giving our computers exactly the same senses and capabilities that we have. right? And that they begin to, in some sense, they almost are getting better. Right? They're, sense of touch. Well, your tablets now with touch screens. If you're using Windows 8, hopefully you're using a touch screen because it's great. The touch screens, there's accelerometers in most devices now, so they know when they're moving. There's GPS, they know where they are. They have microphones, so they can hear. About the only thing we don't routinely seem to have in our devices right now is a sense of smell, although I know there are people working on those chips, and who knows, maybe we'll have senses of smell. But the key thing is that by giving these devices the same kinds of senses that we do, that they can begin to represent the world in ways that in some sense, sort of blur the distinction between what's virtual reality and what's real. I'm going to show you a project where it sort of looks at that a little bit, but specifically focuses on getting computers to sense more about what people do and how people interact. In this particular case, looking at a different way of doing input using technology that can recognize how your hand moves.
Digits is a wrist-worn 3D hand tracker for gestural interactions on the move. The wrist-worn sensor allows the full 3D pose of the user's hand to be recovered in real time, while removing the need for wearing a data glove that covers the entire hand. The recovered hand pose can easily be used to recognize diverse gestures, even while on the move. Our system can be used in a variety of scenarios, including 3D gaming and augmented reality, where both discrete or continuous hand gestures can be used to control input. As the device is wrist-worn, no line of sight to an external sensor placed in the environment is required. The user can perform subtle gestures while resting their hands on their leg or table. Digits is built using only off-the-shelf hardware. The main components are a wrist-worn infrared camera, infrared laser line generator, additional diffuse infrared illumination, and an inertial measurement unit. One interesting interaction possibility Digits enables is 3D spatial interaction around a mobile device that is seemingly interweaved with traditional touch interaction. Here, the user starts semantic zooming using an in-air pinch gesture and continuously controls the zoom factor with the remaining fingers. Another gesture is used for panning the interface or manipulating an object once it has been selected through touch. Another interesting design space for Digits is eyes-free interactions, where no visual feedback is required to control a mobile device. In this example, the user controls functions of a mobile device while the device is left in the pocket. Here, the user turns on the radio, switches channels by mimicking or turning the dial, changes the volume by moving an invisible slider up and down, and finally answers a call by doing a thumb-up gesture. Digits can also be used for fine-grained 3D interactions, for example, as a wearable gaming controller. In this example, the user mimics a gun with their fingers to shoot targets, and navigates within the virtual environment by performing a grabbing motion and moving the arm, and also selecting objects using hand gestures. We have presented Digits, a wrist-worn sensor that recovers the full 3D pose of the user's hand in real time, while removing the need to cover the entire hand of the user. Thank you.
Of course, it's bad enough now people walking around talking to themselves. Now they're going to do this. All right, I'm not sure that's necessarily going to be a big improvement. But again, part of what we're showing here isn't so much that whether this particular idea or technology is interesting, is the fact now that we can do this kind of sensing, right? And that increasingly we can sense not just motions of your hand or motions of your head. If you use Kinect, there's increasingly we're able to even recognize the motions of your mouth and eyes and so forth, and get a sense of whether you're frowning or not. But the point here is that we're giving these devices the ability to see and to start to interact with the world in some fashion, or to collect data about the world in some fashion. If you come to our research lab in Redmond, for example, and you walk up to the elevator, it will open automatically. That's because we have a camera system that has learned what it looks like when people come up to elevators and want to get on. And it knows the difference between people standing by the elevator and people actually want to get on the elevator. It's really great, actually, because it's funny because the system was down the other day, and people are like going up the elevator wondering why isn't it opening? What's wrong here? Oh, okay, the button. I've got to remember the button. Right? I mean, that's the world that we're moving into. It's a one where increasingly we will be able to do things for people in an active way as opposed to on command, because we can sense the world and we can provide, we can sort of recognize situations and provide answers to that. Now I'm going to finish up with one final comment, which is that we're also sort of getting to the point where increasingly we can do some of the things that we always viewed as kind of very uniquely human. In particular, speech recognition is a really good example of that. I was in Tianjin, China in late October and giving a speech to a group of about 3,000 students and faculty there. And one of the things I've been really pushing on our teams for the last couple of years is to build a system that would let me give a speech in China in Chinese and have that be done automatically. I'm just going to show you a video clip of me doing that on stage. Let's see if I can.
Now, I want to come back to the topic of natural user interfaces. One of the most natural interfaces for people is human speech. And for the last 60 years, computer scientists have been trying to find ways to understand and recognize human speech. Now, at the beginning, when people first started tackling this problem, they looked at it.
So all the text you see there is automatically generated from.
And the earliest systems attempted to take the waveforms that came out of a speaker's voice and match them up to waveforms that they knew represented certain words. Unfortunately, that approach is extremely fragile, partly because everyone speaks differently, but also even a single speaker will often say the same thing differently depending on the other words or the context in which they're speaking. You probably already noticed me doing that. Now, in the late 1970s, there was a major change in the way people decided to do speech recognition. This was work being done at Carnegie Mellon University. And the idea was to use a statistical modeling technique, in this case, hidden Markov model, to make to really be able to take a lot of data from many speakers and produce more robust statistical models of speech. Now, that was a huge improvement. And over the last 30 years, speech recognition systems have become dramatically better than they used to be. They still make a lot of mistakes. But in limited domains, it's possible to do very successful speech interfaces. So, for example, in the United States, when I call my bank, I'm talking to a computer, I'm not talking to a person. The computer can answer simple questions about my bank account, or if necessary, it can connect me to a real person if I have a significant issue that I want to discuss. I'm sure you've heard of Apple's Siri product, which answers simple questions. Microsoft Connect has a robust speech interface that allows you to control the interface, and it even allows you to issue commands in the middle of games. Still, these systems have a lot of errors. And the error rates for arbitrary speech have been in the 20 to 25% range. Well, a few years ago, researchers at Microsoft Research and the University of Toronto came together to develop another breakthrough in the field of speech recognition research. The idea that they had was to use a technology in a way patterned after the way the human brain works. It's called deep neural networks. take in much more data than had previously been able to be used in the hidden Markov model, and use that to significantly improve recognition rates. So that one change, that particular breakthrough, increased recognition rates by approximately 30%. That's a big deal. That's the difference between going from 20 to 25% errors, or about one error out of every 4 or 5 words, to roughly 15% or slightly less errors, roughly 1 out of every 7 words, or perhaps even 1 out of every 8. So it's still not perfect. There's still a long way to go. But I think you can see that we have already made a significant amount of additional progress in the recognition of speech. Now, one of the problems that we've also been trying to solve for 60 years is machine translation. And again, in just the last few years, the combination of statistical techniques and big data have allowed us to do a much better job than we previously were able to do in being able to translate web pages or other kinds of information into other languages. For example, today, Big Translate, which is Microsoft's translation system that comes out of Microsoft Research, Big Translate translates millions of pages a day for users into their native language. It's an extremely heavily used service. Now, if I want to have what I'm saying be translated into Chinese, we can take the text that comes from my voice and put that to a translation system. It really happens in 2 steps. In the first instance, we take the English and we convert it more or less word by word into Chinese text. And I think pretty soon we may see that up on the screen. So what happens is we're basically taking the English text and pushing it through the translation system. We then have to reorder that text in Chinese because the word order in Chinese is not the same as the word order in English. To produce something that begins to resemble something that a Chinese speaker might say.
So it's been going in Chinese on the side here. So.
And we're converting them into Chinese text. Now, the last step that I want to be able to take in this process is to actually speak to you in Chinese. Now, the key thing there is we've been able to take a large amount of information from many Chinese speakers and produce a text-to-speech system that takes Chinese text and converts it into Chinese language. And then we've taken an hour or so of my own voice, and we've used that to modulate the standard text-to-speech system so that it would sound like me. So what you see now is the result of that change. I'm speaking in English, and hopefully you'll hear me speak in Chinese in my own voice. Again, the results are not perfect. There are in fact quite a few errors.
结果并不完美。
So there's much work to be done in this area.
在这方面有很多工作要做。
But this technology is very promising.
用这个技术很有希望。
And I hope in a few years that we'll be able to break down the language barriers between people.
数年后，我们希望能够打破人工之间的语言障碍。
Personally, I believe this is going to lead to a better world.
我个人认为这将导致更好的世界。
the presentation today.
希望今天举行其他的讲座。
Thank you.
That was a really fun demo to do. That was really fun. One of the things that was at the end there, because we were piping everything through the speaker system, I had to be very careful not to step on myself speaking in Chinese. So that's why I was carefully waiting after each sentence, because in the try that I did the night before the rehearsal, I had a tendency to speak too long, and then the system would just start to translate, and that was fine, except now I was talking over myself, so it didn't work as well. What was interesting about that particular thing was that it was a very emotional thing for the Chinese students. That surprised me a little bit. I thought people would think it was interesting, but literally there were some students crying, because in some sense, sort of the sense now that we're really beginning to be capable of breaking down this fundamental human barrier in communication, I think overwhelmed some people, so it was fun. And I think the entire speech I gave, that was only a snippet of it. We ran it through our speech recognition system. I mentioned that the standardized error rate that we normally would see in a standardized test is about 15% for that system. For my speech, it was 7%. I mean, it was incredibly good. It was way better than the human translators were capable of doing, during the same period of time. So I thought that was really exciting too. It gives you a sense of we really are on the cusp of being able to address some of these really critical issues. All right, let me change gears one more time. If I can figure out how to get past this thing. No. There we go. Get past it. So the last thing I'm going to do is and this is more specific to my being here at UCL today, is to talk a little bit about what we do with universities. One of the principles we've always operated under is to not just move the state of the art forward in computer science, but to help the larger community do the same thing. And we felt it was particularly important to be able to support research, to support faculty and students in the academic community as well. Over the years, we've had very strong programs for faculty and PhD scholarships, and for supporting basic research, in the university environment. One of the things that we've done is to try to work with universities in different parts of the world. And one of the things I'm very pleased to announce today is that we have established a joint UCL Microsoft PhD scholarship program. We had a competition between where people submitted proposals, professors submitted proposals, for that program. We had almost 24 proposals submitted, really fabulous ones, and 4 were selected. And I'm going to just quickly go through the 4 professors who will be getting these PhD scholarships to use from Microsoft and UCL. First is Professor Jan Kautz. I may not get everybody's name pronounced correctly, who's doing work on 3D reconstruction of live scenes using multiple heterogeneous mobile depth cameras. Professor Sebastian Riedel, doing probabilistic databases of multimodal and universal schema. Professor Jad Alglave, doing work on weakness as a virtue. And you can see this is cross-disciplinary as well. It's not just within computer science alone. And also Professor Benny Chain, and his work on experimental and computational studies of the human antigen-specific T-cell repertoire. And I know some of those people here today, so if you could come up, if you are here, and you can come up on stage, that's great. And if you're not here, then we won't. Is anybody here from that? Okay. Congratulations. Congratulations.
Thank you.
I think we're supposed to take a picture. Because if you don't have a picture, then you weren't really here. Come on up.
I always add to a scene that.
That way we'll know you're here too. Probably want to scoot in a little bit.
Thank you.
Great. Thank you all. Thank you. And like I said, Microsoft is great. Very pleased to be able to do that. And with that, my speech is done, but I'm happy to take a few questions.
Well, I understand that I have a responsibility to sort of chair the question and answer.
Oh, chair the question and answer. You're supposed to intimidate them so they don't ask bad questions? Is that the idea?
Well, or protect you.
Oh, protect me. All right. And we have some microphones, too, so if you've got some questions. If you want to talk about Star Trek, I've got a Star Trek tie on. So I'm happy to talk about science fiction.
I'm very grateful for to see some of these amazing demos. And I visited Redmond and saw the at TechFest and saw some fantastic things. But my favourite moment was standing outside the Microsoft house home in Redmond, and we stood in front of the front door with a group of scientists. And there was a pause, and then there was a slightly lengthy pause, and our guy turned to me and apologised, said, "I'm sorry, but I think the doorbell has a memory leak." So with that, questions? Yes.
Thank you. I'm sure you can't tell us about all the really exciting stuff, but of current developments, what are you most excited about, and when can we expect to see it?
Let's see. So I could go into many different areas. I think one thing this work that's going on right now in deep neural networks, I think, is really, really exciting. The rate of progress in that particular research area right now is just astronomically fast. It seems like every week or two, someone has a new, really interesting new result. So we've seen, and you just saw an example of some incredible improvements in speech recognition technology that really start to make the transition from kind of an interesting thing to really being useful. We're seeing significant improvements in object recognition using deep neural networks. It's been used for some pharmaceutical applications at the University of Toronto, and it looks like it's a really interesting new way of doing certain kinds of machine learning tasks. And that's pretty darn exciting to me right now. I can see, the speech recognition in particular. We're not currently seeing, as we add more data into the system, we're not really currently seeing, anything but linear improvements. And we haven't seen that in 10 years. I mean, the last time we saw any improvements in speech was 10 years ago. So suddenly that area is just changing very rapidly. In fact, one thing that's really exciting about that work is that it looks like these deep neural networks are capable of dealing with a lot of issues of noise and with different types of data simultaneously. So one of the experiments we've been running, which looks really promising, is we're taking speaker data not just from a single language, but from many languages, feeding it into the same network. And we're actually seeing improvements in a specific language's recognition rate, even with data from other languages. And what that's telling us, or we think it's telling us, is that some of the underlying intermediate representation that's being done within the network must somehow be representing some aspects of the human vocal tract, because that's really the only thing common across these different languages. So that's a really exciting area right now. But I could just, if you get me going, program generation is another area, automatic program generation. Just huge improvements happening in that space. Very, very interesting progress right now. The new version of Microsoft Office and Microsoft Excel has a feature called flash fill that's actually based on automatic program generation. So the way that feature works, if you haven't seen it, and I do recommend you play with the new Office 2013, but you have, let's say you have a column of data and another column of data, and now I want to do some transformation. Maybe I want to put brackets around the thing, or change the phone number to have a different representation. In the past, you'd have to write a formula or a macro to accomplish that task, effectively do a little bit of programming to do it. What flash fill does is if you give it an example or two of the transformation that you want, and by just changing the cell, right, it will then do the rest of it for you. And basically the way that works is that it generates, it looks at the inputs and outputs, and it generates the optimal program that with the inputs you've given and the outputs you've given produces that result, right? And then it will just complete that. And if it makes a mistake, if there was ambiguity, make a fix in the place that's a mistake. It'll write a new program and it'll all work. Really cool feature, but just the tip of the iceberg in terms of what we're now able to do in terms of being able to take and generate programs automatically. So that's another really, really fascinating area. But boy, almost every area of computer science, the rate of change right now just seems to be off the scale. And it's really, to me, that makes the whole field so much more exciting. That there's so many problems that we have wanted to solve for so many years that suddenly look like they're within reach. That within 2 or 3 years we may actually be able to do speech recognition as good as a human. Right? That's, I think, now within reach. Maybe it's not 3, maybe it's 4, but it's not going to be that much longer. There's another question in the back.
In setting direction for Microsoft research, do you ever turn to science fiction novels and say, oh, we can try and do that, we can try and do that?
First off, I am a big science fiction fan, and I know a lot of science fiction writers. I'm actually a character in a science fiction novel. There's a science fiction novel called Slant, written by Greg Bear. He's an award-winning author, and it's won the Hugo and the Nebula Awards. And in the book Slant, there's a character named Nathan Rashid. It's an amalgam of the gentleman that hired me at Microsoft, originally Nathan Myhrvold, and myself. If you knew the two of us, that's kind of a weird combination. It's funny because he'd asked me if it was okay to use my name, and then a year or so later, he sent Nathan and me email, and he said, my publisher really wants a written release. Okay, and I started, why does he want a written release? This just seems pretty simple. But I read the book, and I can see what was going on in the publisher's mind, because there's sort of a lot of sort of cyber sex, and it's a kind of a cyberpunk kind of book, and so but the good news is the character that I'm half of in that book, just saves the world. So I mean, it doesn't. There's nothing really funny going on, but it's quite amusing. I actually gave the keynote address at the Science Fiction Writers of American Nebula Awards as well, because people know me in that community. To get back to your real question, I don't really set the research direction for Microsoft Research. I don't think that's really what management does in a research organization. The most important thing that I do, besides, I certainly try to inspire people, and I talk to people, and I've got my own area of expertise. But the thing I really try to do is to just make sure we hire really great people, and that if necessary, we fire people, because in some sense it's who you have that makes a research organization great. It's not what people are working on. If you have great people and you give them an environment which they can be successful, you'll have great work done. And that's really the most important thing. And I always take everybody do I inspire people with science fiction? I do take everybody who works for me out to every new Star Trek movie. I've done that since the very first Star Trek movie in 1979, when I was a professor at CMU and I had only 2 graduate students to pay for it. Now when I do it, I take out 500 people and their families and friends. I rent out an entire theater complex. This is on my own personal pocket. And the only thing I can say there is the good news. I dress up in a Star Trek outfit every time. And I greet people at the door. And the good news there is that my level of income has grown with the size of the group that reports to me. So I can still afford to do it. But it's a lot of fun.
It's better, I guess, to be a character in a science fiction novel than to be a character in a British campus novel.
There's a very spirited defence of blue skies research, but you still have to make choices in what you proceed with and what you don't. So take fetch climate, for example. Why not fetch crime or fetch healthcare or other things?
Well, but I guess the point I would be making there is that I don't make those choices. Our researchers make those choices. They make the choices of what they do. They make the choices of what they don't do. Obviously, they work with the product teams. They work with researchers in academia. It's not like they're operating in a vacuum. But I think that gets back to you hire great people with great taste that can make. I mean, often the difference between a great researcher and a good one is their ability to pick good problems to work on, and to some extent also their ability to know when to stop working on it and move on to something else. And I think that's sort of the way I look at it. I mean, occasionally I'll see someone get stuck, and then we try to help them move on. If I tried to make these kinds of choices, I would just make mistakes. I mean, there have been researchers that have come to me, with proposals, and I don't mean proposal in the financial sense. I mean, just they wanted to talk to me about their work, because we don't have budgets, by the way, for researchers, and we don't have proposals, so we just don't have a bureaucracy that deals with that. And and they'll talk to me about their work and what they're planning to do, and in the back of my mind, I'll be thinking to myself, oh, God, that's a bad idea. I mean, people have been beating their head against that wall for such a long time, I can't imagine that's ever going to work. But I try really hard not to show that. And in fact, I try to be pretty encouraging if I can. And quite frankly, I mean, there have been times when that's happened, and then the person went on to do just amazing work, and solve a problem that no one had been able to do before by looking at it differently. And there are times when there were what I thought were really great ideas that just ran into a brick wall. So I think, if you make too many choices, if you try to make lots of choices at a management level in an organization like that, it just doesn't work.
So we have a question over there.
Okay.
First of all, thank you very much. Just in regards to the Fetch Climate big data show, I think what you said is very interesting, that with big data we are only able to resolve also society issues. The Fetch Climate thing was done in Silverlight, so a proprietary software. And I just wanted to basically know, how is the standpoint of Microsoft Research on openness, releasing data and tools, maybe for free or to use for everyone? Because I, as a student, for example, I'm a little bit limited, at least at UCL, because I have to buy Microsoft products. And what's your standpoint? Like, where will this go? Will these things need to be in the public domain? How are you dealing with the patent issues? Because we're also reading about the patent wars between Google and Apple. And is this actually, as a researcher, is that a problem for you, or can you deal with it just fine?
Yeah, I think we deal with things like that fine. I mean, at the end of the day, corporations create intellectual property and value, and that's allows us to make money so we can pay for people. So it feels good to me. I think to get back to your other point about a lot of so Microsoft to some extent has been deprecating Silverlight, and we're moving to HTML5 and JavaScript platform. A lot of the development that gets done today on Windows 8 app development is being done in JavaScript and XML5, and also can use C# and XAML, but those are also fairly open technologies. So I think that's the sort of the direction of all that work is in that space. Microsoft Research does release a lot of the code and the systems that we produce. Good examples of that include things like the ChronoZoom work that's been released, and that's some joint work that we've been doing with Moscow University and with UC, the UC system in California. The work that we've done on originally the Terra server and Sky server, and then the Worldwide Telescope. All that work has been made publicly available, and people can access it, modify it. The data is available as well. All the fetch climate data is being made available to anyone who wants to get access to it. There's some kinds of information that we can't really provide people that we have access to internally. Those are things like personal data about people. So we have to be very, very careful about things like that. But for most of the scientific work that we're doing with scientific communities, that's very public. All the work we've been doing on AIDS, for example, out of David Heckerman's group, all that's been made freely available to the AIDS community. We run servers and make that software available to those teams. So we do work pretty openly with the academic community, and we publish our work very, very aggressively. I mean, Microsoft Research is the #1 publisher of basic research in the field of computer science, period. I mean, there's no other organization comes even really pretty close anymore, either in academia or in industry. And so we're very aggressive about making our knowledge available to others and making that available. So
Brad.
Just thinking back to your own history in research in computer science, working as an operating system researcher and computer systems researcher, you come to take in a much broader view of a lot of research activities that span not just computer science, but look outward into other disciplines as well, and sort of application of technology in novel ways to produce new research results. I'm just curious, personally, do you remain as excited about developments in core computer systems research as an area as you were when you were a professor at CMU, or do you feel that much of the energy and excitement has moved on to the breadth in the other areas that you're looking at?
Well, I mean, we could get into my operating systems work. I mean, I think I think there's a lot of exciting stuff going on there. So and it's all sorts of different areas. I mean, one of the things that's been really exciting is this notion now that we can literally build systems of hundreds of thousands of machines and do things effectively with it. I'm not sure if you're familiar, but we've recently been publishing work coming out of Microsoft Research in the systems area, where we've set new records for transaction processing speeds that were just blew away anything anyone had ever done before, using very new techniques in terms of how you manage large-scale networks and how you connect local and remote storage. In fact, we've been able to, some of our research has been able to show that we can get local disk access speeds, in a large-scale computing environment, even though the disks are in fact remote. And that's just really exciting. It's just a new way of thinking about the network fabric and network infrastructure that connects those things. There's lots of new work in sort of programming these large-scale systems. Obviously everybody's familiar with things like MapReduce, but there are also new ways of thinking about managing sort of communication graphs and processing graphs and being able to bubble up information in those structures. So actually, there's very little in computer science that I don't get pretty excited about. My actual PhD thesis was in computer vision, right? So even though I'm known for operating systems, I still occasionally get pulled into computer vision work, and I've published in a lot of different areas over the years. I like doing all this stuff, and I think there's a lot of really good, exciting work done, in those areas. Security, privacy, just really exciting right now. Lots of new ideas about how to define privacy, how to think about security, that really are sort of fundamental new ways of thinking about the problem, not just new techniques. So lots of good stuff going on there.
So with some of these latest sort of advances in machine learning, things like the Connect and the translation and the speech recognition, how much do you think that's down to sort of developments in machine learning techniques, and how much to do with the fact that the availability and amount of data that they've got access
It's really fundamentally both. I mean, there have been fundamental changes in the way we do machine learning, whether it's, things like deep neural networks the neural networks have been around for a long time, but this new approach to neural networks called deep neural networks or deep learning is a very recent phenomenon. And in fact, the very first paper published around that subject was about 2006, but in fact the first useful result was a Microsoft research paper working with at the University of Toronto, and that was 2009. And in fact, the really good results, which all represent tweaking in how all that gets done, have only happened in the last 12 months. So big changes in algorithms. I think, yes, part of the reason we're more successful now with some of these techniques is because we've got more data to feed into them. So if you look at machine translation, for example, we now have language models that are gigabytes in size. I think the standard language model we use in Bing Translate for some of the major languages is about 4 to 16 gigabytes in size. We could never have done that before, right? We wouldn't have had the computers to run it on, we didn't have the memory to run it with, and we didn't have the infrastructure to be able to deliver the translation data. So it's a combination of the two, but there have been fundamental, algorithmic changes, both in Bayesian inference, in deep neural networks, in other forms of machine learning that have also been important to making the transition. So it's a combination of things. It's not just one or the other.
Well, I apologise. We've got more questions than we can deal with in the time available. I'd like to thank Rick very much indeed for his talk and for his stimulating answers to the questions. So. Thank you very much.